Indiana University East Chemistry C360, a microscopic interpretation of entropy. Looking back at the Boltzmann factor, while the rest of this seems fairly straightforward, the entropy definition includes this factor W here, which we stated earlier is the multiplicity of the system. It is the number of ways that a system can be arranged to have the same overall state. Now this overall state we're going to refer to as a macro state. So that really tells you how many molecules there are, and moreover, it's going to tell you how much energy there is. So the real question is, how do we find W and how do we define it? However, as we mentioned before, a system will have a discrete number of energy levels. And it really depends on how the molecules are arranged. Ultimately, we can't measure the exact quantum states of each system. So that's what the case is. So let's think about two molecules, molecule 1 and molecule 2. So these are our two molecules, and we have 2 joules of energy overall. If I put it in energy level 0, it'll have 0. I put in energy level, this energy level here, put in this energy level here, I have 1 joule. Here, the only way I can achieve a total of 2 joules of energy is if I put both molecules on this energy level, and there are no other ways I can do this. There's only one microstate corresponding to this macrostate. And therefore, the multiplicity is equal to 1. In contrast, here, I have 2 joules in my upper level of energy. So, in order to achieve this macrostate, I need to put one molecule in this lower energy level and the other one in the higher one. But what's not to say that I can put molecule 2 down here and molecule 1 here. In this event, therefore, each of these is a microstate. And therefore, there are 2 microstates corresponding to this overall macrostate. And therefore, the multiplicity here is 2, and the entropy of this system is Kb ln of 2, where Kb is the Boltzmann constant. At absolute 0, it is worth thinking about this, because for a perfectly crystalline solid, there is no motion for the molecule. There's only one way for a perfect array of atoms to be arranged. So therefore, as a result, W is equal to 1, so S is equal to Kb ln 1, which is equal to 0. And therefore, we reach what's known as the third law of thermodynamics. For a system that consists of a perfectly crystalline matter, the entropy is 0 and absolute 0.